Good morning, good afternoon, good evening. Welcome to my talk. My name is Robert, and I'm a Google developer expert for machine learning and the Google Cloud Platform. Today, I'll be speaking on programming microcontrollers. I'll begin with an introduction to what microcontrollers are. A microcontroller is essentially a computer, but it's not a computer in the sense of what we're used to when we think about computers. Typically, when you think of a computer, you think of a desktop or a laptop, or maybe even a tablet or a mobile phone. And yes, those are all computers. But when we think about them, we think about all of the things that we can do with them. And that's the differentiator between a microcontroller and a general purpose computer. A general purpose computer is capable of doing multiple things. So if you think about the desktop, you could use it for video editing. You could use it for spreadsheets. You could use it for sending email, for browsing the internet. You could use it for watching movies or listening to music. The same thing applies to your tablet. Same thing applies to your mobile phone. You can make calls with your mobile phone, but you can also play games on your mobile phone. Well, as long as it's a smartphone. And if it's a smartphone, you can listen to music. Think of a wide range of things. We have app stores for most mobile devices now, and you have lots and lots of apps there that let you do multiple things. So, in that sense, these devices are general purpose. However, when we talk about microcontrollers, we're talking about something that is application specific. So, typically, a microcontroller will be programmed to do only one thing. Now, another difference between a microcontroller and a general purpose computer is that with your general purpose computer, you have inputs provided by the user, either with a keyboard and a mouse in the case of a desktop or a laptop, or via the touch screen, or maybe some side buttons in the case of a tablet and a mobile phone. And then for your output, you typically will have a screen, and then you'll have text output. You could also have sound if what you're listening to is music. However, when you come to microcontrollers, the input and the output are via what we call general purpose input and output pins. And the input and the output are usually some sort of electrical current or voltage. And these are directed via the pins. Inputs are via sensors, or the input could be from another microcontroller. So you're able to daisy chain microcontrollers where the output from one microcontroller serves as the input to another microcontroller. Microcontrollers, by extension, can control other microcontrollers, or using their output pins, they're able to control motors, actuators, LEDs, and anything that can be controlled via electricity. So if you look at the use case for microcontrollers, we have them embedded in other applications. You typically wouldn't go out and just purchase a microcontroller the way you would purchase a general purpose computer. But there are lots and lots of devices within the home that have microcontrollers embedded within them. So if you think of any device or any gadget within a household that is smart, chances are it has a microcontroller inside of it. So let's talk about why you would want to program a microcontroller. Well, let's start with the fact that you're already programming computers, you're programming phones. So why not program microcontrollers? There are billions of microcontrollers out there. Again, they're embedded in devices, but think about all of the devices you have in a smart home, or even if those devices aren't smart, washing machines, refrigerators, air conditioning units, they all have microcontrollers in them. So manufacturers are putting microcontrollers inside of these devices, and someone needs to program them, right? So why shouldn't it be you that is programming these microcontrollers? So if you think about examples of devices that have microcontrollers in them, we have a wide range of them. Within the house, you have fridges, washing machines, microwave ovens. These all have microcontrollers inside of them. If you think of the smart home, you have door locks, cameras, speakers, doorbells, set-top boxes, and even televisions that are smart in and of themselves, so they don't need an extension. You also have wearable devices. So examples of these are smartwatches, headphones, or earpieces that are smart. We have smart rings, and we have eyeglasses. Within healthcare, you have devices that are either handheld or wearables that help with monitoring the health status of individuals. And you also have industrial applications of microcontrollers. Now, all of these things we have up on the screen are not exhaustive. They're just examples to give you an idea of where you might find microcontrollers out in the wild. So now we get to how to program a microcontroller. Now, typically, most microcontrollers are programmable using either C or C++. There are some exceptions to that, and that doesn't mean that you can't program them with C or C++. It just means that you're able to program them with other languages besides C and C++. So first things first, you need at least the foundational knowledge of C and C++ in order to program a microcontroller. But you're also able to program some microcontrollers with other languages such as MicroPython and CircuitPython, as well as embedded Java. And there's also a variant of JavaScript. So there are some microcontrollers that let you program them using JavaScript. Now, because microcontrollers control other electronics and they themselves can be controlled by other electronic in terms of the inputs, you need to understand some electronic circuits. Now, it goes without saying that if you work with code and computers, you should be fine with reading documentation. Microcontrollers tend to come with extensive documentation, so you need to get comfortable with reading documentation as well as with the specifications for the microcontroller boards that you'll be working with. Finally, you need to have a love of making things. Now, when you think of microcontrollers, for getting started, there are various channels or routes that you could use to get started. There are some boards that are out there for educational purposes, and examples of these are Microbit, Arduino, Raspberry Pi, Sparkfun, and even Sony makes microcontroller development boards. There are other more professional manufacturers for these boards, but let's focus on the learning side for now. So we're going to take a look at an example pinout diagram for a board. So typically, this is how boards would be documented for purposes of programming. There's a more extensive documentation that goes into the actual processor and the programming. But in terms of input and output, there's usually a pinout diagram because, again, you communicate using pins. And the example on the screen is a Raspberry Pi Pico. It's a microcontroller development board. And we can see here that it has 40 pins, 20 on the left and 20 on the right. And you can see how these pins are labeled. They're color-coded and they have numbers. So, for example, if you look at the green numbers on the left, you have GP0. all the way down to GP15. Now there are 20 pins, but only 15 of them are labeled. And then you have 4 of them that are called ground. And think of ground from an electrical perspective, where you've got live and neutral. So that ground is like a neutral wire, doesn't have any voltage passing through it. Now, if you look at the color coding to the right side of the screen, you'll see that various colors are for various things. So there's red for power, and what that means is you can get power from the board using the pins that are specified with that particular color code. Now, you also need to understand the voltage that is being output. So you'll notice that pin 36, for example, outputs 3.3 volts, right? You'll see the light green is for general purpose input and output. And then there are some other colors. For example, there's orange for debugging. And if you go back to the board, you'll see that the debugging pins are at the bottom of the board. So there are other things, and they're more electronics and communication specific. So things like SPI and I2C are things that you'll get conversant with once you go into the electronics. So if you already understand electronics, then you'll know what these communication protocols are about. So for this workshop, we're going to look at a wake word detection example. And we're going to be doing that using the Sparkfun Edge development board. The Sparkfun Edge development board has been made available to us by Sparkfun Electronics, and we've already given these out to participants of the workshop. So if you already have this, or if you got it from somewhere else, feel free to follow along with the workshop as we proceed. We're going to be utilizing tiny machine learning, and we're going to be deploying a model onto the Sparkfun Edge development board. And this process is an intersection of 3 things. First of all, there's electronics from the Sparkfun Edge development board that we're going to be working with. There's embedded programming from the firmware that you're going to be writing. Although in this workshop, we're not going to write it, we're just going to deploy it. But there's programming, embedded programming, and then there's machine learning. And the machine learning component is the machine learning model that we're going to be deploying onto the Sparkfun Edge development board. So the goal of the exercise is to illustrate to you the use of machine learning inference on the edge, on a device that isn't connected to the internet with constrained resources, but the model that is going to be deployed to that device is going to be small enough to fit into the memory of the Sparkfun Edge development board. So let's look at what is required to program this wake word detection example. On the one hand, to train a machine learning model, you're going to need to collect data. And then you're going to need to train a natural language processing model. And that typically will be done using TensorFlow on a desktop. And then you're going to need to shrink the model to fit on the microcontroller. And this requires the use of TensorFlow Lite and TensorFlow Lite for microcontrollers. On the side of the microcontroller board, you're going to need to write an embedded program. You're going to need to transfer the model from the desktop environment into the embedded program. Then you're going to need to implement a pipeline so that you can stream data from the microphone that is on that microcontroller board into the model. Okay. And then you're going to need to compile all of that and flash it onto the microcontroller. Now, for the purposes of this workshop, the left side has been handled for us because it would take just too much time to go into all of that. And the right side, the first three things have also been handled for us. So what we're going to do is compile and flash onto the microcontroller. That in itself takes a little bit of time, so it's perfect for a workshop in these settings. So we're going to go into the workshop now, and what we're going to do is we're going to set up our software development kit such that we'll be able to compile our firmware and flash it onto the microcontroller board. We have we have links up on the screen that you can follow to learn more about all of the things that we're discussing right now. So I've switched over to a terminal window and I'm programming from Mac OS, but you can follow along with documentation from Sparkfun website if you're using some other operating system such as Windows or Linux. So from the terminal, the first thing that I'm going to do is I'm going to install what is called the new toolchain. So it's a C compiler toolchain, and I'm going to be making use of brew. So the first command is brew install cmake. When this completes, you'll need to run the next command, which is brew tap. And when that completes, the final command for the toolchain is brew install. Okay, and if everything works as expected, you should be able to run this following command, and this works fine. The next thing that you need to do is do a git clone of the Ambix Suite SDK. That's the SDK that comes with the Sparkfun Edge development board. So you'll want to do your git clone into a folder that you've set up specifically for working with the board. I already have a folder called Sparkfun, as you can see. And I've gone ahead and run my git clone. I already have it downloaded, so it's not going to download a second time. And what you want to do is set up an environment variable called amb_root to make it easy to work with. And the way to do that is to put that into your environment file. So you can put that in your bash profile. So you can see that on this line, I have exported amb_root, and it points at the location of the GitHub repo that I just cloned. Now, if you do that, you're going to want to run source so that your terminal recognizes all of your environment variables. Right. Now, We're ready to work with our board, but before we do that, let's check our serial port. And the way to check the serial port is to list the devices. It's going to be called something like CU. So what you need to do is list /dev/cu asterisk. So that will list everything within the /dev folder that starts with CU. So we see now that the only thing that we have is this Bluetooth incoming port. So once we connect our board, it should show up as a second port. So I will cut over and connect the board, and then we can see what our serial ports that are listed will look like. So I've got the Sparkfun Edge board, and I've got a cable that's connected to my computer. Once the board is connected, it starts to flash. And the reason why it does that is there's already firmware on the board, and this helps you with the sanity check, so you're sure that your board works. So back within our terminal, if we run this command again, we see now that we have a second device that is listed there. So we have our serial port, and that's what we will be working with going forward. Now we're ready to go ahead and compile an example and deploy it onto our board. So to do that, let's change location to our Ambic root, which is what we downloaded. And you can go ahead and list what you have in there. And what we're interested in is in the folder called boards_sfe. So I will change into that location. And if I list that, I will find a folder called Edge, which is where we have files for this particular board that we're working with. So I will change into Edge, and I see that I have an examples folder. So I will navigate into that examples folder, and I will list what I have. So you can go ahead and work with any of the examples in there, but for the purposes of this workshop, we will work with the micro speech. So I will change into the TensorFlow micro speech folder, and in there we will have a GCC folder. Feel free to read the README file, but I will go into the GCC folder, and in there I will type make clean, and that has completed without any error, and we're now ready to flash our firmware onto the board. And to do that, I will paste this command. What we need is make. We need to specify our COM port, and from what we had up there, we have /dev/cu dot USB serial. I'll just scroll back up and copy it actually. So this is this. And I need to pass in a parameter that tells it what bootloader to use, and that's the Ambic bootloader. And then we need to specify the baud rate. The baud rate is the communication speed, and you'll be working with 115/200. Now, if you have a Sparkfun Edge board and 115/200 doesn't work for you, then you need either 921-600 or 460-800. So to flash the board, you have a specific sequence. Our board is already booted up because we have that flashing light. So what we need to do is hold the button at the bottom, which is button 14, and then wait a second and then press and hold the reset button. And I haven't pressed it yet, but once I do, you'll notice that the blue light will stop flashing. And then I'll go ahead and release the reset button while still holding on to button 14. Now, back on the screen, you'll notice that I typed in the make command, but I didn't hit enter. So I will, at this point, go ahead and press enter on the screen. And okay, so that worked. I can go ahead and release the button 14 that I was holding on to. And the code has been flashed onto the board. And what I need to do now is reset the board. And I can do that by pressing the reset button. And the board is flashing. It doesn't look like anything has changed, but actually it has flashed the firmware onto the board. And I can go ahead and try saying yes and no. So we've come to the end of this workshop, and what we've been able to show you is why you should worry about machine learning on microcontrollers, why you should program microcontrollers, and we'll show you an example of flashing a binary onto a microcontroller. We know that we didn't go into the nitty-gritty details of the code itself that gets written onto the microcontroller, but we will get into examples of how you can write the code for these in future sessions.